Good.
Okay, sorry. Yeah.
You want to introduce the
So you want me to start, or you want to introduce?
So hi everyone. So today we have Michal Heller. Am I pronouncing your name correctly?
Yeah, that's correct.
From a new affiliation, Ghent University in Belgium, telling us about entanglement of purification and reflected entropy in CFTs. Thanks so much for accepting the invitation. I'm looking forward to the talk. Go ahead.
Yeah, thanks guys for inviting me. I'm very happy to give this talk. And let's make it as interactive as possible. I will use whiteboard. So, well, I mean, like, let's see, like, where we get. In principle, I mean, I should be able to cover the full material, even if you pop up questions very often. This talk is based on, roughly speaking, two papers. One written in September 2020, and the last one written in February last year, as well as some work in progress with Eric Tony and Lucas Hackl. So let's start with my whiteboard so that I can tell you what this is about. So, sorry, wrong whiteboard. Not used to my iPad. Yeah. Yeah. Okay, very good. So in the course of the past several years, I have been interested in things in the context of ADS-CFT and at the intersection with quantum info that are not well understood on the quantum field theory side. So I think most of us would agree that you know, HRT and entanglement entropy are pretty well understood on both sides of ADS-CFT. And the things that I have in mind that I have been interested in and I have been pursuing are related to novel geometric observables that were considered in the context of ADS-CFT only in the course of the past 4 or 5 years. So one of them is our holographic complexity. So these things are related to codimension 1 objects in the bulk. So the idea is that if we have ADS, say 3 geometry, this is some constant time slice. This constant time slice defines a state in the dual holographic conformal field theories, or in this case, it might be the vacuum in some holographic CFT in 2 dimensions. Then you know, like you consider say a maximal volume slice in this geometry. This is a covariant observable on the gravity side. It's associated with some property of the state, and well, the conjecture is that this property is complexity. And when you think about it, you realize that this property has not been really well understood in the context of quantum field theory, and that opens a lot of avenue for interesting research. So that's like one thing that I've been doing in the course of the past 4 years or so. So when Nima asked me to talk about whatever I find exciting, I was very much tempted to give you some thoughts on complexity, but then I realized that that's not necessarily what you're doing. And then I thought that like the other thing that I'm quite excited about actually that is much closer to what you guys seem to be up to is related to the other interesting / novel quantity, which is entanglement wedge cross section. So if we look at the same picture, but now sort of from the top, so we look at the you know, constant time slice, like this is again like t equals 0, but viewed as from the top of this picture. And again, like say we are in the vacuum of holographic 2-dimensional CFT. And now in this vacuum, we consider 2 subregions. So like one subregion is going to be A, the other one is going to be B. So for 1 + 1 dimensional conformal field theory, these are just intervals. then entanglement wedge looks, roughly speaking, like this. And these are of course Ryuta-Kanagi surfaces, or like that's going to be like Ryuta-Kanagi surface associated with the situation. And now one entanglement wedge is like the interior of this. And one novel geometric quantity that you can consider is the cross section of the wedge. So basically the length of this segment here that I'm drawing with green, right? So this guy, entanglement wedge, is an interesting geometric entanglement wedge cross section is an interesting geometric quantity in ADS CFT. It's covariantly defined, and it must be associated with some property of reduced density matrix of these, two interval or this bipartite system in holography, right? And the question is, of course, with what property you want to associate it. And in 2017, Takanagi and his collaborators suggested, and in parallel, I think Brian Swingle and other group of collaborators, and the references are in the works that I did, suggested that entanglement wedge cross section is related to entanglement of purification. So I'll be more specific about what this quantity is and how to define it, because that's going to be the main player of the talk. Around 2018, Tom Faulkner and collaborator basically showed that the entanglement wedge cross section is going to be 1/2 of the quantity called reflected entropy. And I think around the same time, entanglement wedge cross section was shown by the people at U Chicago in spherically symmetric situations. I think probably in the vacuum of ADS to be related to logarithmic negativity. I think it's denoted by epsilon. So there are various candidates for field theory interpretation of entanglement wedge cross section. And in my talk, I want to focus on these two quantities. And the statement that I want to make is that these quantities are actually not very well understood in the context of quantum field theory itself. So what I want to do, and like this was the goal of these publications, is to understand them a bit better in the case of possibly simplest non-trivial quantum field theories, which are conformal field theories in general, and in particular in 2 dimensions. And the quantity that's going to be actually the most mysterious is this entanglement of purification, because this one not only is going to be concerned with purifications, but also is going to be concerned with optimization over various purifications, and such optimizations are typically quite hard to perform, are quite challenging to do.
Can I ask a question?
Yes, of course.
So you mentioned that entanglement of cross-section, entanglement wedge cross-section is covariantly defined.
Yeah.
So you say the definition is that it's the extremal surface that is anchored on the 2 RT surfaces. Is that how you define it?
I think so, yeah.
Okay, so there is a min-max in there as well.
I think so, yeah.
Okay.
Yeah.
That's
yeah.
Thank you.
Yeah.
And then you mentioned something else. When you said that the connection to log negativity of the stuff that Shinsei Ryu and Franz talked about.
Yeah.
You said that is true in vacuum. Is there some sort of evidence? I mean, what is the extent of the proposal? Is it? I thought it was supposed to be true in general, or at least the proposal was saying it.
I think there is a proposal, and there's evidence for this proposal. And I think for this evidence in this proposal, the calculation was, to my understanding, at least like in the paper from 2019, I think it was vacuum and maybe a thermal state. And then, okay, there might have been more evidence, but I haven't followed it very much. In fact, I found this paper only this week when preparing for this talk. So So yeah, I'm not really sure. Anyway, the punchline from whatever I had to say is that this logarithmic negativity is not that. I mean, from the point of view of being able to calculate this logarithmic negativity might not be that hard ultimately to calculate because it doesn't require purifications. Now, reflected entropy require canonical purification, so to speak, and I'll be more specific in a moment. And entanglement of purification requires purification and optimization. So this makes it a pain in the neck to deal with in the context of quantum field theory. So as a result, like if we can derive some universal statements about entanglement of purification in particular, that's very nice. That's basically solving a hard problem one way or the other, and that's basically the goal of these two papers that I mentioned. So in the following, I'm not going to come back to ADS-CFT very often. I'll just focus on quantum systems and introduce like various bits for whatever I have to say next, right? So I'll be interested in these in density matrices. I'll be interested in purifying density matrices. And then I'll come back to the situation that we are interested in, which are so I will be interested in density matrices in general, and then in mind I'm going to have a situation in which we are in a CFT, not necessarily in 1+1 dimension, and we have like subsystem A and subsystem B in the vacuum, and we're going to be playing with what is the form of say entanglement of purification in this situation. But like part of the story is supposed to be quite general. So the standard situation in which we have a mixed state, I mean, the standard one, like the canonical example of a mixed state is a thermal state. So when we think about the thermal state, right, like what we have is we have a normalization by the partition function, and then we have sum over energy eigenvalues, Boltzmann weights, and projectors onto the energy eigenstates, right? So that's a thermal state. And for such a thermal state, there's a way of representing it as a pure state in an enlarged Hilbert space. So what we do is like we take a product of this original Hilbert space with its exact copy, and as probably all very well know, maybe even much better than me, the standard purification can be denoted as a so-called square root purification, also known as the thermophile double state, and it's going to be given by basically taking a square root of the Boltzmann weight. So we're going to have like -1/2 beta E. And now we have a state in an enlarged Hilbert space. So like two copies of the same, of the original Hilbert space. We entangle each energy eigenstate with itself with a weight that is given by a square root of the Boltzmann weight. And then there's a altered normalization that guarantees that this thermophile double state is a unit normalized state in the enlarged Hilbert space. And now the idea is that we started with one system. We noted it as like left system. That's if you want to embed the thermophile double state in holography, you would also have like the right system, like the right boundary of the thermophile double state of the eternal black hole. And anyway, if you take this thermophile double state, and of course, if you take a trace with respect to the left or the right subsystem, then what you're gonna get is gonna be a thermal density matrix, either in the right or in the left. So indeed, the thermophile double state is a way of purifying thermal density matrix to an enlarged Hilbert space, which consists of two factors of the original Hilbert space, one of which we associate with the original system. So what I showed to you was on an example of thermal field double state, but there's nothing really specific about thermal field double state. Like the same can be achieved for any density matrix. In particular, we can achieve the same for the density matrix that we are interested in, which is going to be the reduced vacuum state over with two intervals in which we are interested in, right? So we're going to have a density matrix that encodes information about two subsystems in a CFT, and we're going to be interested in purifying it in this canonical way to a situation in which I'm going to be calling square root of rho, in which we're going to have like the original factor in the Hilbert space A and B, as well as these auxiliary factors that guarantee purification. And now, of course, like if we take a partial trace with respect to A prime and B prime, we're going to be recovering the original density matrix. So is it clear what whatever I have been trying to say so far?
Yes.
Okay. So now I'm telling this, of course, because I want to introduce the notion of reflected entropy and entanglement of purification. So the idea is to introduce an interesting measure of correlation between A and B in terms of this purified state. So I mean, we don't want to use rho AB. The reason being that, well, I mean, there we already have mutual information that's going to be a great quantity to consider. We don't want to consider A prime B prime, because that, by the purity of the full state, that's going to give rise to similar properties as AB. So sort of what we want is we want to mix A and B and A prime and B prime with each other. And to this extent, the proposal is to consider the reduced density matrix upon tracing out like the subsystem B and subsystem B prime, or the factor B prime. So we do this at the level of now, like bipartite system in any quantum mechanical system in which this decomposition makes sense. And if you have problems with thinking about it in the context of quantum field theory, then of course the way to go is to think about quantum field theory as arising from some lattice discretization and define these quantities into lattice discretization. So this reduced density matrix is going to be an important player in this talk and this whole construction. The reason being that the fundamental entropy of this reduced density matrix is gonna, by definition, give rise to the reflected entropy. So the idea is that like we purify our system in a canonical way. In the copy of the system, there is a realization of A, and this is A prime. In this copy of the system, there is a realization of B, and this is B prime. We trace out in this purification B and B prime factor, and left with the reduced density matrix obtained from a pure state. We use entanglement entropy as a measure of correlations, and this is the definition of the reflected entropy. And now that's not the only thing that you can do. The way to obtain entanglement of purification, or that's not going to be entirely precise. What I'm going to say now is the following. So when we have this big state, square root of rho, on this state, we don't want to act on A and B, because there we have a fixed density matrix that we don't want to alter. So we're going to act with an operator that is an identity on let me denote identity maybe with, not to confuse with mutual information. Let me denote identity by ID. So we want to argue with identity on AB, but then with some non-trivial unitary on A prime, B prime. So such an operation is not going to change any properties of the subsystem AB, but if you, for such a state, if you consider a reduced density matrix A and A prime, this reduced density matrix is going to be in principle a functional of this unitary that you introduce in your subsystem, right? So now when you evaluate your von Neumann entropy, this von Neumann entropy is going to depend on this unitary that you applied, and what you can do still is to minimize over all possible unitaries acting on A prime and B prime. And the result of this minimization is the entanglement of purification. So the way to construct both quantities is quite similar, and there's a caveat, and I'm going to mention the caveat now. That is, like, you construct canonical purification. In this canonical purification, you identify a copy of A being A prime and a copy of B being B prime. And now you either take a trace of B prime and compute the fundamental entropy of the resulting density matrix, and that gives you this gives you the reflected entropy. Or alternatively, before you take a trace with respect to B and B prime, you still apply a unitary in A prime, B prime. So you apply a unitary acting on this factor in purification that you have to create to purify the system. So this unitary does not affect the original density matrix, but it affects entanglement between A and A prime and B prime, and B and B prime, A prime and B prime. So in particular, it's gonna alter the entanglement entropy for a subsystem A prime, and the minimization over this unitary is gonna give rise to entanglement of purification. So the caveat here is that I assume that there are no ancillas, right? Like when I create this purification, I assume that the dimension of the factor A prime is the same as the dimension of the factor A, and similarly, the dimension of the factor B prime is the same as the dimension of the factor B. In principle, I can purify to a system to a state like with many ancillas on top of what we had initially, and then this unitary can act also on these ancillas. So whatever I showed you so far assumes that there are no such ancillas, and some of the results that I'm going to be showing you assume a possibility of ancillas, and some of them assume that there are no ancillas. And the results that assume possibility of ancillas are consistent with the absence of ancillas. So that's why I presented it that way. Yeah, any questions about this so far?
I have a question. So A, E, and A prime, B prime, they are like symmetric, right? Because of the
yes. Mm-hmm.
So in that case, this minimization, although you said we don't want to change the things in AB, we can still replace with UAB, right?
Yes. So alternatively, you can construct a purification optimize over AB.
Okay.
And the result is going to be the same quantity. I mean, the minimization is going to give rise to the same quantity. Yes. In fact, like this is, I think, something that my collaborators implemented in their numeric for some reason of convenience that I don't recall the details, but it was convenient for them to define optimization, I think, this way.
Okay, thank you.
Yeah, thanks. Okay, anything else?
Sorry, I also have a question. Is there any constraint on U, A prime, B prime? Right? Or is it any general unitary operators?
I would say that's any general unitary.
Okay.
And the picture that I always have in mind is a picture of finite dimensional Hilbert spaces. So I'm thinking about spin systems. And in this context, I have in mind the most general unitary that you can consider.
Okay, thank you.
Yes. Okay, very good. Yep. So so we did two things. So let me mention one thing briefly because it's based on numerical considerations. And I don't think that this is the most interesting thing. So when you look at holographic entanglement I mean, if you believe in identification of the entanglement wedge cross section with entanglement of purification, you can of course compute it and make a prediction. So there was this prediction in the situation in which, well, when we are in a, again, like in a two-dimensional CFT. Let's be now a bit more general. We are in the vacuum, and we consider a situation in which we have like interval A and an interval B that are adjacent to each other. Okay. And now, like we construct entanglement wedge associated with these two objects, and entanglement wedge cross section, as far as I remember, is going to be basically. So I was consistently drawing this with green was this guy, and now obviously you can calculate the length of this guy using ADS3 geometry. Just by doing a simple analytic optimization problem, and you're gonna get an answer, and you're gonna get a formula, and I'm gonna display this formula in a moment. And now there is also like this procedure of path integral optimization that the Kyoto group introduced in order to basically define complexity in quantum field theory in terms of the geometry that underlies path integral representation of states in quantum field theory. And so like this, I'm gonna show you on slide. And in 2018, the people in Kyoto published a paper in which they were able to reproduce the green the entanglement wedge cross section. So like this object, they were able to obtain the result from the path integral optimization approach. So, I mean, it's not really a purpose of my talk to introduce the path integral optimization, and there's a separate paper that discusses it, and probably there's a talk on the web that really describes how to do this. But the point that I want to make is that path integral optimization is not really a systematic procedure of the, say, status of the replica trick in CFTs. It's still a research program in development that is not entirely understood. So, you know, like, even though like that, it allows you to reproduce something in the context of ADS3 CFT2, it would be very nice to have an independent check in general CFT. And the thing is that like this, the path integral optimization does not really rely on the CFT to be holographic. It's supposed to apply to a general CFT. So in particular, it's something that's supposed to apply to a free CFT. So in a paper in 2020 with Tadashi and collaborators, we look at this quantity in free conformal field theories. So like just to on the lattice. So just to put everybody on the same footing, and I hope you can see my screen now. We're going to be interested in a lattice realization of a 1+1 dimensional CFT. So in this context, I'm talking about free fermions or free bosons. And for the purposes of this talk, you can think about, and this part of the talk, you can think about free fermions as being the Ising CFT. Now, we represent the system on a lattice. We have two subsystems. So these subsystems are going to enclose some number of lattice sites separated by D lattice sites. And now we're going to purify. So we're going to purify in the language of lattice degrees of freedom. So we're going to forget about quantum well, basic quantum field theory description. We're going to just operate in terms of lattice degrees of freedom. So in terms of spins or free Fermion degrees of freedom or bosonic degrees of freedom, and say in this figure we see a subsystem of size 3 and another subsystem of size 3. So like in total we consider 3 plus 3 sites. Now what we do is like we purify this to a pure state. So the whole state is a vacuum of a critical system on a lattice. We consider 3 plus 3 site subsystems separated by some distance. We take it as an input for a many-body procedure. So we forget now about quantum field theory, lattice system, etc. We just think about the purifications into some auxiliary Hilbert space that introduces also a factor of A prime and B prime. We apply this unitary transformation to A prime and B prime and optimize to calculate entanglement of purification. So we did it numerically in two cases for free bosons and free fermions for two adjacent subsystems. So the separation between the subsystem is 0. And what we looked at is entanglement of purification as a function of the subsystem sizes, right? So we kept the two subsystems to be adjacent to each other. But if you say decide to have, I don't know, 10 lattice sites in total, then for 10 lattice, here we consider 12 sites. So when you think about 12 sites in total for A and B, then you can decompose these 12 sites in total into A equal 1 site and B equals 11, or A equal 2 sites and B equals 10, etc., right? And then we just do all the evaluation numerically. And as a result, what we see is a clear pattern. And this clear pattern follows exactly the analytic prediction of the path integral optimization program, which is a C/6 logarithm of the product of the interval lengths divided by the size of the total size of the intervals times lattice regularizer. So basically the results in this paper in the context of entanglement of purification can be thought of as a corroboration of first the entanglement of the path integral approach to entanglement of purification. Secondly, for the association of the entanglement wedge cross section with entanglement of purification. So like this work played two roles, and because the prediction when two intervals are adjacent to each other is supposed to be entirely universal based on the path integral optimization procedure. Indeed, like we were able to corroborate it by doing free fermion, free boson analysis. And what's important, why this is important? This is why this is important that these are free systems. For free systems, you can use Gaussian techniques, and Gaussian techniques make purifications much easier, because the size of the Hilbert space does not grow exponentially with the subsystem size, but rather as a polynomial. And as a result, for reasonably big subsystems, you can actually do these purifications very efficiently on a desktop scale computer system. So these optimizations can be very efficiently implemented. Yes.
So this is a CFT calculation. So I would imagine what you're plotting is sort of like you're plotting a function of a cross ratio, right?
Yes. Yeah.
So in terms of the cross ratio, because it's hard for me to imagine what these variables, omega A, WA over WA plus WB are. In terms of the cross ratio, what is the behavior like? So is it like as you approach the cross ratio 1, when these regions touch, is it growing up? Like how does it grow? Do you have do you know?
So this result is when the subsystem touch. So I don't move them apart, like they are literally touching each other. I just change the relative size of one versus the other.
The reason I'm asking this is that Cassini and friends did use Gaussian techniques to calculate the reflected entropy directly in for free scalar and free boson, and they plotted in terms of the conformal cross ratio, and of course it peaks. I'm just wondering whether this has the qualitative same behavior or not.
No, that's a good point. I don't have these results on top of my head, so I would have to compare. But like I mean, for the purposes of the next transparency, we actually did look at this paper by Bueno and Cassini, and we translated their results into this formulation in terms of W and separation. And at large distances, we match. So. I mean, it doesn't really answer your question, but yeah, I'm like what I'm trying to say is that there's a clear-cut way to go back and forth between this.
Their calculation was the reflected entropy, but you calculate entanglement of purification, right? They cannot compute.
Good. So in this paper, we focus on entanglement of purification because we were thinking, well, we wrote the whole paper about optimization over Gaussian states. In the subsequent work, we look at both quantities. And reflected entropy, of course, is easier to calculate reflected entropy is easier to calculate than entanglement of purification because it doesn't require any optimization. So in fact, like the starting point for this calculation for every data point is reflected entropy calculation, but we just didn't store like the first data point in the optimization. Because like we start at the canonical purification and we start applying unitary, and like this takes us away and lowers the value of S prime.
What I'm trying to get to is that could you identify a regime where the behavior of reflected entropy and entanglement of purification were different? Because I mean, you guys are you've done the only calculation I know of where you compute both, right? So the question is that are they qualitatively ever different in your
good. So what I'm extrapolating a bit, but I'm pretty confident about what I'm going to say. So I think the statement for this two interval adjacent setup is going to be that reflected entropy is going to be twice entanglement of purification, and they're going to match in the respective comparison to the holographic predictions in this particular setup.
Actually, a factor of 2? Is that what it is?
I think so. Yes.
Oh,
Yes.
Okay.
Because I would say that I mean like this is our result for entanglement of purification, and then there are Tom Faulkner's results for association of the entanglement wedge cross section with reflected entropy.
Right.
Which is supposed to be exact in time reflection symmetric invariant states, so in particular in the vacuum. Since his calculation is supposed to work generally, and here we have a comparison in this particular setup that also works, I think the reflected entropy is going to be just a factor of 2, this expression that I'm showing. So instead of C over 6, I would expect C over 3 here, and the rest holds.
I guess I was not aware of the calculation of Faulkner you're mentioning. So I didn't know that there is a result that says in quantum field theory, in some class of states, they're off by a factor of half. I thought, yeah. Is there such a result?
No, I'm talking about this particular, no. I'm talking about this particular setup where, so in this particular setup, there is a prediction, numerical prediction that we have that agrees with path integral optimization, that agrees with entanglement wedge cross section. And these are 3 calculations that agree with each other.
Right.
And we don't go back and forth between 2 sides of holography, right? Like we just did 3 calculations and they all agree with the same formula.
Okay.
And then there's a calculation by Tom Faulkner and collaborator in which they identify the reflected entropy with half of the entanglement wedge cross section, right? So what I'm saying is that here, because we know that entanglement wedge cross section is entanglement of purification in this particular case, what I'm saying is that if you were to show entanglement reflected entropy, it would be different by a factor of 2.
Yes. Thank you.
For sure. Yeah. Good. Yeah. So let me proceed. So far so good. So this is numerical, and numerics is nice, but well, I also like to do analytic stuff. So let's switch gears a bit and let's talk about analytics. So go back to the iPad. Yeah. Can you see my iPad?
Yes. Well.
Okay. Yes. So I just changed the page so that we start in a clean situation. So so maybe let me provide the crucial formula. Yeah. So now yeah, I mean, like, the setup is going to be the same. So the setup that I have in mind is supposed to be 2 subsystems in a vacuum of a CFT. One is going to have a size W, the other one is going to have a size W as well. So you should think about these subsystems as spherical. So I'm going to draw them for 1 + 1 dimensional CFT, and they are separated by a separation D. And this is what I will be concerned for the rest of my talk, which is the situation in which this separation D is much bigger than the size of the individual subsystems. So like, this is subsystem A and this is subsystem B. So we're going to basically look at a large distance limit for the density matrix rho AB. But before I do this, I just want to quote an expression, and you can derive it in a very simple fashion. And this is a general expression for any purification that you can consider here. And the expression is that when you take S A prime, it's going to be bigger or equal than 1/2 of IAB. As a result, like, if you know the behavior of mutual information, is going to provide a bound on this entanglement A prime. And as a result, like, it provides a bound for both the reflected entropy as well as for entanglement of purification. So if we're going to run into any doubts about possible behavior of reflected entropy or entanglement of purification, we're going to come back to this bound and use it to rule out outstanding possibilities and to focus on a single one. So that's going to be the idea. And you can derive this relation using strong subadditivity of entanglement by looking at this 4-partite system A, B, A prime, B prime. It's actually very easy. So I'm not going to do this. Back to business. So I want to look at a large separation limit for these density matrices. So what I'm gonna assume, and that's gonna be the input, and this input is gonna be is gonna be valid in lattice constructions of lattice regularizations of CFTs. So, for example, for the Ising model, it's gonna work beautifully. And it is that when we look at the density matrix in AB, this density matrix at large separations is going to have a form of a sum, infinite sum, in which the leading term when the separation is infinite is going to be a product of density matrix in A and a density matrix in B, so that the systems become completely decoupled, right? And this is consistent with the fact that, well, in CFT, there are long-range correlations, right? But I mean, they are long-range, but they still nevertheless follow as a power law. So like at large enough separations, like these correlations are not going to be there anymore. And then I'm assuming that there's a gap in the operator spectrum. So the lowest lying primary operator is going to have a dimension delta. So the correction to this expression is going to be the correction that covers information about the two-point function of this operator O delta. And we know that this two-point function of an operator delta is going to scale, and I'm introducing here W for dimensional reasons, as 1 over the distance, 1 over the separation of the subsystems to the power 2 delta. And then there's going to be some, there's going to be some contribution to density matrix that I'm going to denote as rho AB1. And I know at this point very little about it, and I'm not going to need to know much about it. And then, there's going to be maybe a second lowest lying operator in the CFT, et cetera. And then in this expansion, so there's going to be some terms here sitting. And at some point in this expansion, you're going to hit a term that corresponds to 4 insertions of operator O delta, so lowest lying primary, 2 in one subsystem and 2 in the other. And the term that you're going to get is something like this. And I'm going to call this guy rho AB 2. Okay. And then there's going to be higher order terms. Okay. And now what's going to be important for some of the things that I want to show is that, of course, when you take a trace of this density matrix with respect to, say, subsystem B, and similarly for A, then of course you get like rho A. So rho A, so this rho A is the same as this rho A, right? So as a result, from this, you already infer that whatever these corrections to the product density matrix are, they're going to have a property that the trace with respect to A or with respect to B, for all these terms with n bigger than 1, bigger or equal 1, are going to be 0. The reason for it being simply that already the density matrix that we need in this case is there from the outset. So that's going to be a property that we're going to use in a second. Any questions about this so far? So maybe one thing to say is that okay, I'm in the CFT, such statements might be a bit shaky because of possible UV divergences, etc. However, when you are on a lattice, such statements make perfect sense. And actually, if you take Ising model, and in Ising model for at least small subsystem sizes, you can evaluate rho AB. And what you can see is precisely this sort of behavior. So actually, in our derivation, we started with the Ising model. We saw the structure, and we took it as a starting point for more general considerations. Yep. Okay, so just to give you a flavor for the behavior of reflected entropy and entanglement of purification in this setup, I'm going to give you a bit of a flavor for the behavior of mutual information. So let me start with first law of entanglement. So something that Nima knows extremely well. And basically the statement is that if we consider a von Neumann entropy of rho plus delta rho, so delta rho is some perturbation of the density matrix, right? And this guy is going to be given by, well, to the linear order is rho, but then the first term, the term linear in delta rho is given by a very simple expression, or in principle a very simple expression, which is logarithm of rho. delta rho and a trace of this guy. And then there are higher order terms. Let's look at SAB from this perspective. So related to it, like from this we can infer the properties of the mutual information. So for us, like this, maybe I should put here an index or not. So for us in the setup, I mean, I want to think about this delta rho as all these terms basically. So like this, I would think about. Or maybe I'm exaggerating a bit. Let me be a bit more precise. So for me, like delta rho for the star is going to be this term. Okay. So this is delta rho, and that term for the moment is going to be rho naught. Okay. So I'm going to calculate the change in the entanglement entropy coming from the presence of this connected term in the density matrix that connects A and B subsystems. And that's very easy to do using this expression. And the thing is that when we look at the modular Hamiltonian, we have like this rho naught that is factorized. So rho naught is going to be a factor of rho A times rho B. As a result, like when we look at the modular Hamiltonian is going to be log of rho A, and I'm agnostic about minus signs and things like this, because that's not important, times identity on B plus identity on A times log of rho B, right? So this is the form of the modular Hamiltonian that we get from the zeroth order. And now, in order to evaluate this expression, we will be taking a trace over AB. This trace is going to have delta rho 1, right? So this is this term times the modular Hamiltonian. But like this modular Hamiltonian always going to have an identity either on A or on B. And we know from this property that trace of the correction to the density matrix with respect to A or with respect to B is going to give us a 0 because we already have like the background density matrix in subsystem A or in subsystem B encoded. So as a result, this shows that the leading order non-trivial behavior of the entanglement entropy for two subsystems is going to come from corrections. It's not going to be linear in delta rho. So as a result, it's going to come from the terms that sit here. So from one of these terms, not from this one. So this we rule out. So we can run a similar argument for the subsequent terms all the way to this term. So to the term that behaves like W over D for delta, where delta is the dimension of the lowest lying primary. So as a result, like the statement that we would be tempted to make is that the SAB is going to be whatever it is in A and whatever it is in B, because that's like the leading order contribution. And then we know that the correction is going to be at least of the order W over D to the power 4, right? And now, on the other hand, yeah. So somebody wanted to ask something.
Yeah, it says it's for delta, right?
Yeah, of course. Sorry. Yeah, well spotted. Yeah. Thanks for paying attention. For delta, yeah, exactly, right? And from this we can also, right, we we can calculate the mutual information in a trivial way by subtracting it from SA plus SB. But the important thing is that the mutual information is supposed to be bigger or equal as a correlation between A and B squared. So in a sense, we know that the W over D2 delta is the least allowed fall-off of the quantity that we are after. And this is like the leading term that can contribute. Therefore, this quantity has to behave in this particular way. So this is a way in which one can use very simple lattice arguments to show that the mutual information indeed has to behave as something that is of order of W over D to the power 4 delta. By first ruling out the appearance of lower order terms, and then showing that the remaining term that can contribute is the one that's gonna give rise to that must give rise to a non-trivial contribution, that must come with a non-trivial prefactor, non-zero prefactor. Was it clear, or was it a bit too fast?
It was good. I don't know. Other questions?
Okay. So we want to apply a similar logic to the behavior of reflected entropy or entanglement of purification. So the idea is the following. So let me introduce a shorthand notation. So I'm going to introduce the epsilon delta, and this epsilon delta is just a shortcut form for this quantity. So again, like we're going to look at the density matrices. So like this rho AB is going to be rho A product rho B. Then there's going to be some term that is first order here, and it behaves like epsilon delta, linear in epsilon delta. And then there's going to be some contribution that I think we define with a factor of 1/2, but that's not important. Sorry. So that's like the term that cares about the 4-point function, etc., etc. And now similarly, I'm like having this form, we can construct purifications. So we construct a general purification. This general purification is going to have a form of A prime, B prime. And it's also going to have this expansion in epsilon. It's also going to, this epsilon is a small parameter, and the small parameter is going to live its life also at the level of purification. So there's going to be a 0th order purification, and the 0th order purification doesn't care that subsystem A and is entangled with or correlated with subsystem B. So this guy is going to be just some product state. Let me use other letter. Some state phi in A prime, tensor some state. I'm not even sure. Maybe it's the same letter but different symbol. B prime, right? So this state, this is the leading order purification, and it doesn't care about the fact that A and B at non-infinite distance are correlated, right? And then there are corrections, and these corrections are non-trivial. And so there's like epsilon delta, and there's some vector that we add, and there's epsilon delta squared, and other vector. Okay, so this and it keeps going, and then there might be some terms in between that we're not gonna care about for reasons similar to the reason that I already didn't care about such terms before. And this is the general structure of the purification that you can that you want to see. And again, by doing studies in the Ising model, you can corroborate for 1+1 spin subsystems, you can corroborate this finding by looking at the exact form of the density matrices and purifications. So indeed, like this is going to be the structure of the purification that you see.
Question?
Yes, of course.
So here, the expansion you're writing for psi seems to suggest that if I take this vector and look at the reduced density matrix of it, so I'm going to get the tensor product state, but then I'm going to get a whole bunch of reduced density matrices that correspond to psi1 and psi2 and such things, right?
Yes.
That appear at order epsilon squared, right?
They appear at order epsilon and epsilon squared, yes.
Epsilon delta, yeah. So, but this is obscured because of the fact that, like, the delta AB2 that you're writing in the first one, in the expansion of delta AB, it's not an actual density matrix because the trace of it is not 1. Right?
Yeah, I guess that's true, but you can. Yeah.
Go ahead.
Yeah, I mean, like good. So I guess like what you're saying is you're raising a question if the vector phi1 and phi2 are really normalized, and yeah, sure. I'm like their normalization has to be fixed by the normalization of the full state that you want to be 1. So yeah, indeed, like raw AB1 and raw AB2 should not be thought of as density matrices, normalized density matrices.
Yeah,
right.
Right, for sure. But then there's also the fact that I think the connection between vector psi and the row AB1, 2, 3 are somewhat obscure, right? Or is
no, it's not. It's non-trivial. Non-trivial.
Okay.
No. You have to construct. You have to. That's a very good point, Nima. So you have to construct. From this purification, you have to construct the density matrix and take trace, and that's going to give you the relation between this raw AB. So this term and this vector, etc. Okay. Yeah, sure. So anyway, so again, I'm like in the end, like we're interested in raw A prime, right? And this is given by trace B prime from this big guy, right? It's like so from the, well, let me just call it psi, right? And this psi is of course is defined in the whole thing. And now imagine that you compute this this density matrix, right? So and you diagonalize it. So it's going to be a huge density matrix for subsystems that you might be interested in the context of field theory limit. So it's going to have some eigenvalues, some mu10, etc. Right? And these eigenvalues actually, at the zeroth order. So the terms order epsilon delta to the power 0. The eigenvalues are very simple because the starting state was a product state, right? So like the density matrix in A and the density matrix in B didn't know. The raw AB was a factorized state. So as a result, like the purification is going to reflect it, right? And the state raw A prime is going to be actually a density matrix of a pure state as well. So at leading order, like this mu, one of the eigenvalues is going to be 1, and all the other ones are going to be 0. So like that's the leading order expression, and like there's nothing really fancy about like that's trivial. That has to be the case because of this factorization at large separation. Now, at the first order, in principle, there can be a correction, right? So you might write that, like these eigenvalues are going to be proportional. So let's say like there's some alpha j here, epsilon. And here you're going to have something like 1 minus, sum over these alphas times epsilon. However, if you think about it, I mean, like we think such term should not be there because such term in principle you can think about epsilon as a real parameter, and then you see that there's something funky happening when epsilon changes sign, which is that these terms can change sign. And when these terms change sign, it's not good because we're talking about eigenvalues of the density matrix. So we expect all the terms to be a non-negative definite. So based on this, we don't want such terms. And if such terms are not there, then, and in numerical calculations, we indeed reproduce this result, such terms are not there, then the leading contribution to the eigenvalues is going to come at the order epsilon squared, epsilon delta squared. So these eigenvalues are going to be something like 1 minus alpha total epsilon delta squared, and these other ones are going to be, some coefficients epsilon delta squared. And then there's going to be higher order terms that we don't care about. And now it's actually very simple to use the exact expression for the von Neumann entropy, right? Which are going to be the SA prime, regardless of the purification, is going to be minus sum over all these mu's, mu log mu over all mu's. So let's introduce an index a lowercase a. So that's like just the definition of von Neumann entropy. And now when you expand this expression in epsilon, what you're going to find out is that this SA prime is given by this coefficient alpha total, epsilon delta squared log of epsilon delta to the power minus 2 plus a term that is proportional to epsilon delta squared. So the leading term that you get from this consideration is this one.
Sorry, another question.
Yes.
So the logic that you have for the largest eigenvalue, I agree with. But when you talk about mu of j larger than 0, the other eigenvalues, right? Why are they order epsilon squared? Because the first one you say that it can't be larger than 1, right?
Yeah, but the other ones should be also non-negative, right? So what I'm saying is that if they make sense for
you're right. Thank you. Yes.
Yeah, because there are also probabilities, yeah. So anyway, so what I'm trying to say is that from these very simple elementary considerations, you get a leading order expression for possible behavior of SA prime. And I haven't made any assumption if this is after or before optimization. So this is completely general, assuming the form of the density matrix that I took as an input. And now comes this expression, this wonderful inequality, which is that SA prime. Sorry, let me be consistent about coloring. Yeah. SA prime is bigger or equal to 1/2 of IAB. But we know that IAB behaves as epsilon delta squared. So like this is W over D to the power 4 delta. So if this coefficient here, alpha tot, is 0, then we end up with higher power law behavior than the one predicted for mutual information. And as a result, we run into contradiction based on this very general quantum info inequality. Therefore, this shows that this is not only the leading possible behavior of the of SA prime, but this must be a general behavior, no matter what's happening in any system that satisfies such a decomposition of a density matrix. So therefore, since I didn't make any assumption about SA prime being the reflected entropy or being the entanglement of purification, this really proves that the behavior of these quantities at large separation of both of them in any CFT for which the starting point was correct, so in particular for any CFT on a lattice with a gap in the operator spectrum, is going to be W over D to the power 4 delta log of W over D. Or in other words, these quantities at large separation, so this is at large separation, these quantities behave like they decay like the mutual information, but their decay is enhanced with respect to mutual information by a log of an inverse of a mutual information. Okay. So this is supposed to be very general. So the only assumption is our starting point that we expect to be obeyed generally on the lattice. So well, so far so good. So you can ask, you know, how is it really realized if you look at the actual models, and in particular, our analysis here does not tell you anything about the prefactor here, apart from the fact that it has to be some non-negative number, but it doesn't tell us like what this prefactor really is. So before I just conclude, let me show you a slide. Yeah. So in this paper, where this abstraction was presented, we again looked at two examples of conformal field theories on the lattice. One was free fermions, the other one was Ising spins, and in these quantum many-body systems, we calculated mutual information just for sport to see that at large separations, we get the behavior that CFT predicts, and we do. I mean, like this is what it shows. And then we look at the reflected entropy, and we for free fermions we reproduce the results of Bueno and Cassini that Nima mentioned at some point during this talk. And for Ising spins, well, I mean, like we produce our own results and reproduce the formula that we predicted as an analytic prediction. So indeed, like in these two cases, we have a great match with our functional prediction for the large order behavior. And well, it's not strange. I mean, the assumptions that we put into our derivation hold here in both of these theories. So these calculations, because we also achieve numerical convergence with respect to the ratio of, with respect to the subsystem size, can be also thought as giving a very good indication of the prefactor in the scaling. So I mean, I run a bit over time, so I don't want to take too much longer. I mean, let me just reiterate the most important lesson, which is that by doing explicit numerical calculations, we confirm the behavior of entanglement of purification and also trivially reflected entropy for the setup of two adjacent intervals for free conformal field theories with formulas expected to be valid in general for arbitrary central charge. And subsequently, we look at this situation with very large separation, so like very large distance between subsystems in a general CFT on the lattice. And we predicted that the behavior of reflected entropy and entanglement of purification should be, in general, enhanced with respect to that of mutual information by a logarithm of separation. So this was seen for the reflected entropy by Bueno and Cassini, and here we derive numerically similar results for Ising spins, and provided a physics proof that this behavior is generic. And in an outcome paper with Lucas Hackl and with Eric Toney, we're going to be looking at continuum limit for free fermions, like trying to get the prediction for the overall prefactor, at least for the reflected entropy. Yeah, so I think that's all that I had to say. So thanks a lot, and thanks for the questions during the talk.
Thank you so much. Are there questions for Michal here or online? I do have one question. So would you agree with the statement that, so you concluded that in this regime, long distance regime, or when the conformal cross ratio is almost zero, right? You concluded that the behavior is like minus mutual information, log mutual information.
Yes, exactly. Yeah. Yeah, this is what I tried to show on my iPad. Yeah. So this is precisely this.
Yeah. Okay.
And we were surprised because, like the entanglement of purification requires this optimization over purifications, and in quantum field theory, I mean, it's rather intricate, like how to do this, right? Because in general, in this numerical algorithm, we reside in the realm of lattice systems. So we have a system with, for example, we have say 3 spins, and we add like 2 factors of 3 spin degrees of freedom. So we operate in the Hilbert space of 12 spins. So it's already gigantic, and there we construct general unitaries acting on 6 spins, so like A prime, B prime, doing optimization over these unitaries and minimizing A prime. So what I'm trying to say is that these unitaries, I mean, they are not local. I mean, like, they don't act on, 2 nearest spins or anything like this. I mean, like, there are in principle like a very non-local operations. And I mean, from this perspective, it's a bit hard to imagine like what kind of things you would have to do in quantum field theory, where like you typically live with the paradigm of applying local operators, etc. In order to perform this sort of optimization. I mean, maybe the answer is simple. Maybe like we are doing an overkill, and maybe in the end, like the only thing that you have to optimize involves rather simple inclusion of simple exponences of simple operators in a CFT. But like we didn't really see any indications of this in our numerics, because it was basically a brute force numerical, I mean, maybe subtle numerical calculations, but we didn't really gain any insight about the matrix that does the optimization about this unitary. So I find it actually quite interesting that you can provide a very high level argument that gives you the answer regardless of these purifications.
It also means something interesting. There's some sort of interesting physical implication. So Patrick Hayden and friends have argued that the difference between the reflected entropy and mutual information, or half mutual information, is, they call it the Markov gap, is a measure of tripartite entanglement. Now, in this regime that you're talking about, that is basically controlled by log of W over D minus 1, but log of W over D is very large in your regime. So you drop the 1, and it's sort of saying that in this regime, mutual information is tiny. So the Markov gap is almost the same as reflected entropy.
That's true. Yes. That's a nice way of applying it.
It's quite fascinating. It sort of says that if the Markov gap is a measure of tripartite entanglement, it's saying that there's most of the entanglement in this regime is tripartite. That's what it's saying.
Yeah. That's interesting, actually. Yes.
Okay. Any other questions for Michal? If not, let's thank Michal again. Thank you so much. I really enjoyed it.
Thanks a lot. Yeah, I mean, it was fun, and yeah, I mean, I hope to see you in person in foreseeable future.
Hopefully very soon. All right. Thank you so much, Michal.
Bye bye. Have a good afternoon. Bye bye.